In lesson 2.4, we're going to talk about what's known as the chain rule. And this is a rule for taking derivatives when you have composition functions. Now, when you look at the official definition of the chain rule, what you want to consider is if you have a function that is dependent on another function. So if I wanted to take the derivative of this function y that is with respect to u, but I want to take the derivative of y with respect to x, and u is a whole nother function that's with respect to x, what you need to do to take the derivative of y with respect to x is you find the derivative of y with respect to u and then multiply that by the derivative of u with respect to x. So here is the prime notation for that down here. When we start going through some examples, this will make a little bit more sense. So looking at example 1, we have two functions here. We have y with respect to u, and then we have u with respect to x. So if I want to take the derivative of y with respect to x, I need to use the chain rule. So I'm going to take the derivative of y with respect to u and then multiply it by the derivative of u with respect to x. So when I take the derivative of y with respect to u, that's this notation right here. I'm going to bring the 2 down in front. So that's going to give me 2u. And then the derivative of 3u is 3. Then I have to multiply that by the derivative of u with respect to x. So that's this notation here. And when I take the derivative of 2x minus 9, I just get 2. So I have 2u plus 3 quantity times 2. When I distribute that 2, I get 4u plus 6. But it still isn't listed as the derivative with respect to x yet because we still have this u in here. We want our derivative so that it has x's in it instead of u's. So the last step is that we're going to substitute u in for this u right here, and then we'll have everything in terms of x. So if I take u, that is 2x minus 9, and plug that in, I have 4 times 2x minus 9 plus 6. So this right here was u. Now when I substitute this 2x minus 9 in, now we have the derivative of y with respect to x. And when we clean that up, we get 8x minus 30. So this is our final derivative of y with respect to x. So we have our two interpretations of this. The first interpretation is when you consider this as the slope of the tangent line at any given point. And then we can also look at this as the instantaneous rate of change at any given point. Now, if we want to evaluate that at 5, just like before we plug that in, we plug in x is 5, and then we work that out and we get 10. So when you want to use the power rule, but you have an inner function as your base, then we're going to apply the chain rule and the power rule together at the same time. And this is what's known as the general power rule. So what this is saying is, if I want to find the derivative of y with respect to x, whatever is this inner function, I want to leave that base the same. I'm going to pull the n down in front. I'm going to reduce that exponent by 1 like we normally do. And we have this inner function here that remains the same, but then I need to multiply it by the derivative of u with respect to x. So whatever that inner function is, we multiply by the derivative of it. So looking at example 3, we're going to really start to get an idea of what we're doing here with the inner functions. So for example A, we notice that we have some function raised to the 6th power. Inside here is a whole nother function. This is u of x inside here. And u is being raised to the 6th power. So this inner function is u of x, so when we take the derivative, we need to multiply by the derivative of u of x. Just like before, when we take the derivative using the power rule, we bring the 6 down in front here. Then the exponent gets decreased by 1. The inner function stays the same, but then I have to multiply by the derivative of that inner function. So when I take the derivative of 4x to the third plus 5x plus 2, I'm going to get 12x squared plus 5. Looking at part B, we have a rational function here, but we can use the generalized power rule by rewriting the denominator with a negative exponent. So this is going to first be written as 4 times 6 minus 2x raised to the negative power, the negative fifth power. And now when we use the generalized power rule, I bring that negative 5 down in front. So let's come down here where they show the steps. So the negative 5 comes down in front. So now we have 4 times negative 5 in front. That inner function stays the same. And then I decrease the exponent by 1. And then I have to multiply by the derivative of that inner function, which is negative 2. So now when we clean this up, I can combine the negative 2 times the 4 times the negative 5. That gives me a 40 out front for my coefficient. And then we have our inner function, which is the 6 minus 2x raised to the negative 6 power. So this is our final answer. But if you want to take it further and rewrite this function without negative exponents, you can just flip the 6 minus 2x to the negative 6th, flip it downstairs, and make that a positive 6. Just remember that when you're flipping stuff, don't flip things that don't have negative exponents. Sometimes people forget and flip the whole thing. That 40 isn't being raised to a negative exponent, so that stays where it's at. Now in part C of this example, we have a function that has a radical. So we have the function y is equal to the fifth root of 7x minus 8 quantity to the third power. When you're dealing with radicals, before you take the derivative, you should always put it in exponential form first. So I'm going to rewrite this as 7x minus 8 quantity raised to the 3/5 power. That 5 is coming from the fifth root. We're raising 7x minus 8 to the third power. We're raising that to the 1/5 power because of the root. And then when you raise a power to a power, we know we can multiply the exponents, which gives us the 3/5. So now we have it set up so that I can use the generalized power rule. So I'm going to take the 3/5, bring it down in front. The base, the inside stays the same, so that remains 7x minus 8. Then we decrease the exponent by 1, and that gives us the negative 2/5. That's coming from 3/5 minus 1. And then because we have the inner function here, we have to multiply by the derivative of that inner function. So the derivative of 7x minus 8 is 7. Now when we clean this up and we can combine these two factors here, we have the 7 and 3/5. When I multiply those together, I get 21/5. And then that's still multiplied by the 7x minus 8 raised to the negative 2/5. This is the derivative. However, we have different forms down here. If you don't want a negative exponent, you can flip the 7x minus 8 to the 2/5, put it downstairs as a positive exponent of 2/5. Additionally, another form that you can put this in, if you want to put it in radical form, you can just rewrite it as the fifth root of 7x minus 8 squared. And then of course you want to bring that 5 down as well. Here is an example where we're going to use the chain rule and the quotient rule together at the same time. So in the previous examples, we used the power rule and the chain rule. Now we're going to use the quotient rule and the chain rule together. So looking at this function here, we have a function that is a rational function. So we're going to take and use the quotient rule, but because we additionally have that inner function, we have 2x minus 1 all being raised to the fourth rather than just x to the fourth. We're going to have to apply the chain rule with the quotient rule. When you use the quotient rule, you take the derivative of the top, that's this here, d dx of the top, times the bottom. So we're multiplying this by the bottom. And then we subtract the top, which is 2x minus 1 to the fourth, times the derivative of the bottom, and that's this d dx 3x plus 2. And then that's all over the bottom squared, so 3x plus 2 quantity squared. So this first step right here is just setting it up. So now that we have this set up, so we know what to do, the 3x plus 2, we just carry that down for right now because we're going to multiply that by the derivative of the top. So we're going to take the derivative of 2x minus 1 to the fourth. Because we have this inner function here, we have to multiply by the derivative of the inside. So we're going to be using the chain rule. I'm going to bring the 4 down in front. That's where this is coming from. The base stays the same, so I have 2x minus 1. My exponent decreases by 2. That's where the 3 is coming from. And then I multiply by the derivative of what's inside. And the derivative of 2x minus 1 is 2. So that's where this is coming from. Now the second part, where we're taking the derivative of the bottom and multiplying by the top, if I take the derivative of 3x plus 2, that's just 3, so that comes here. And then the 2x minus 1 to the fourth just comes down here. So now for this part right here, I have 2x minus 1 to the fourth times 3. Once we rearrange and clean this up a little bit, this 2 and this 4 can come out front as a coefficient of 8. So 2 times 4, that comes out here as an 8. I still have this 3x plus 2 right here, and then I have 2x minus 1 to the third. And then for this one right here, the 3 can come out front, and I'm left with 3 times 2x minus 1 to the fourth. And then of course you want to keep carrying down your denominator. If you want to clean it up further, you can go through these steps here that the author of the book has laid out for you. To be honest with you, I would be happy with this, unless the question in XYZ specifically tells you to simplify this. I would be totally fine with this part. So you can take it further if you want or if you need to, but I would be okay with the way it was on the previous slide. Now when you plug in -1, if you want to evaluate it at x equals -1, you're going to get -27. Example 5 is when we need to use the product rule and the chain rule together. So at the beginning of this lesson, we talked about using the power rule and the chain rule together. The previous example we looked at where we would need to use the quotient rule and the chain rule together. This example is going to show us how to use the product rule and the chain rule together. So this function here is defined by the product of two other functions. So I have x to the fifth, that's our first function. And then I have a second function here, which is 4x minus 1 raised to the 1/4. With this second function, in addition to being a product, we have an inner function here that's not just x to the 1/4. So this is why we're going to need to use the chain rule. We're going to first set it up using the product rule, and then we'll go ahead and actually go through and take the derivative. So the product rule says you take the derivative of the first, so we're going to write that out as d dx x to the fifth, and then we multiply that by the second function, so that's this. the 4x minus 1 to the 1/4. And then we add the derivative of the second function, that's this right here, times the first function, so times x to the 5th. Now, when we go to take the derivative of x to the 5th, we're going to get 5x to the 4th. This part right here, the 4x minus 1 to the 1/4, just gets carried down. Now, for the second factor here, we have x to the 5th, that gets brought down. But now you have to take the derivative of the second function, and this is where you need to use the chain rule. So I'm going to take the 1/4 down in front. The inside stays the same. The exponent decreases by 1, so we have 1/4 minus 1. That's where the negative 3/4 comes from. And then we have to multiply by the derivative of that inner function. And the derivative of 4x minus 1 is 4. So now, this is really messy right now. We have it worked out, but it's really messy. So let's clean it up. We have the 4 here. We have this 1/4 here. And when we multiply, we get a 1. And then we have this x to the 5th, that's this here, and then this factor right here that's brought down. Now, if you want to factor it and simplify it further, you can. At this point, I would be happy with this, but you can look at the steps to see how you can factor it and simplify it further. Okay, in this next example, we're going to practice using the chain rule and the quotient rule together again. But in this example, we use the chain rule first. And when we take the derivative of that inner function, then we use the quotient rule because that inner function is a quotient. So when I take the derivative of this, the 4 comes down in front, and then the 3 goes up here because I decreased the 4 by 1. Now I have to take the derivative of that inner function. So I take the derivative of 2x plus 5 over 8x plus 7. This, we're just going to carry it down. And now we're just going to do a little bit of work with this and use the quotient rule. So when we use the quotient rule, we're going to take the derivative of the top and multiply that by the bottom. So we have 8x plus 7 times the derivative of 2x plus 5, which is 2. Now we're going to subtract the derivative of the bottom times the top. So here's the top, 2x plus 5. And when you take the derivative of the bottom, that just gives us 8 here. And then, of course, we take the denominator and square it. So now the derivative is complete here. The next few steps is just going to clean it up and simplify it. So when we distribute the 2 and we distribute the 8, across the top here we have 16x plus 14 minus 16x minus 40. So we have a negative 26. When I take the negative 26 by this top part here, that gives me 4 times 2x plus 5 quantity to the 3rd power. So that's all on the top. Then in the numerator, we have 8x plus 7 to the 3rd, and then we have to multiply it by 8x plus 7 squared in this denominator. When the bases are the same, we add our exponent, so that gives us an 8x plus 7 raised to the 5th power. In this last example, we're going to go over an example of a business application using the chain rule. So in this example, we are given 2 functions. We're given the demand function and we're given the cost function. The demand function relies on the price, so we would plug in the price and get out the demand. The cost function depends on the demand, so I would plug in the demand and get out the cost. However, when we look at the question, we're asked to describe the cost based on the price. So we need to figure out a way to use these 2 equations to come up with a new equation so I can plug in the price and get out the cost. Now, the only way to do that is by using composition functions. I can find cost and plug in d of p, the demand function, and create a composition function where I can plug in the price and get out the cost. So in the cost function, everywhere I see D, I'm going to take the demand function and plug it in right here. So when we do that, we're going to get 20 plus 10 times, now this is where D used to be, but we're replacing it with 420p to the negative 2. So that's our inner function, and then we're raising it to the negative 1/3. That's this negative 1/3 right here. So here's our composition function in which we can plug in the price and get out the cost. So in part B here, and I apologize, it looks like my bulleting didn't work, but this should be part B. It says, how does the cost of production change as the price increases from $50 to $51 per unit? And so we're going to take the derivative of our cost function. This is where we're going to use the chain rule because we have this inner function. When I take the derivative of 20, that's 0. When I take the derivative of this second term, so I'm going to take the negative 1/3 down in front. That gives me a negative 10/3 here. The inside stays the same, and then we decrease negative 1/3 by 1, and that's where this negative 2/3 comes in. But then we have to multiply it by the derivative of that inner function. So when I take the derivative of the inner function, I'm going to get negative 2 times 420. That's the negative 840 here. And then I have p raised to the negative 1/3 because the negative 2 decreases by 1. When we clean this up a little bit and simplify, this is what we're going to get. I took the negative 840 p to the negative 1/3 out front and multiplied that with the negative 10. So that gave me a positive number. And then when I divide it by 3, I get 2,800. And so this is what we get when we simplify it. So now if I want to find the marginal cost specifically at the price 50, I want to plug in the item cost is 50, and what we get out is 0.2416. So this 0.2416, that represents the cost, the change in the cost. It's going to increase by 24 cents when the price increases $1 from 50 to 51.